Right now, Nvidia is the undisputed king of the global economy. The media calls them an untouchable monopoly. But behind closed doors, the exact companies funding Nvidia's rise are quietly deploying hundreds of billions of dollars to engineer its total destruction. To understand how this war will be fought, you have to look inside the machine. The physical materials required to construct the Nvidia B200 Blackwell data center accelerator cost exactly $6,400. The logic processing dies themselves are relatively cheap. The dual die configuration costs roughly $850. The real expense is memory. High bandwidth memory, HBM3E, accounts for $2,900 per unit. That represents 45% of the total cost of goods sold. Fusing multiple dies together requires TSMC's advanced CoWoS-L packaging. That adds $1,100, a 47% premium over previous packaging techniques. Final testing, heavy power delivery components, printed circuit boards, and module-level assembly absorb the remaining $1,550. Total physical manufacturing cost, $6,400. Yet, Nvidia retails this exact hardware to enterprise clients for an average selling price of $40,000. By extracting $33,600 in pure gross profit per unit, Nvidia retains a staggering 84% estimated gross margin. The fundamental bottleneck in the global AI supply chain has quietly shifted away from pure logic processing power. It is now dictated by advanced memory fabrication and complex packaging constraints. Nvidia is extracting software-like margins on a hardware bottleneck. The companies paying this premium are completely cornered. In the second quarter of fiscal year 2026, a single corporate entity designated strictly as Customer A wired Nvidia $10.7 billion. In a single 90-day window, Microsoft accounted for 22% of Nvidia's global sales. Combined with Amazon, Alphabet, and Meta, these four hyperscalers generated an unprecedented 61% of Nvidia's total corporate revenue. In the immediately preceding quarter, these same four buyers accounted for 54% of revenue. The buyer base is rapidly consolidating. The reliance is tightening. The global artificial intelligence infrastructure market is currently defined by a severe structural paradox. The entities generating the vast majority of Nvidia's historic profits are actively engineering the technological frameworks required to dismantle its monopoly. For the calendar year 2025, these exact same four hyperscalers collectively deployed a record $332 billion in capital expenditure. This is a massive 54% year-over-year surge from the record $215 billion deployed the prior year. Individually that year, Amazon committed approximately $105 billion strictly to AI data center infrastructure. Microsoft paced to exceed $80 billion. Alphabet earmarked $75 billion. And Meta increased its infrastructure budget to $72 billion. For calendar year 2026, the spending has accelerated into uncharted territory. Amazon alone announced a $200 billion budget, with Alphabet pacing toward $185 billion, Meta up to $135 billion, and Microsoft exceeding $105 billion, pushing collective capex well north of $625 billion. A substantial portion of these funds is quietly dedicated to financing proprietary custom silicon programs. They are designing hardware to permanently replace Nvidia in their data centers. Every tech giant is secretly trying to destroy Nvidia. The origins of the current technological conflict trace back long before the advent of modern generative artificial intelligence. It is rooted in highly specific architectural decisions and competitor missteps. Nvidia was founded in 1993 during a meeting at a San Jose Denny's diner by a 30-year-old electrical engineer named Jensen Huang, alongside co-founders Chris Malachowski and Curtis Preem. Their initial ambition was strictly confined to accelerating video game graphics through a novel hardware design. Following a severe product failure that nearly bankrupted the company in 1996, Nvidia successfully pivoted. They developed the modern graphics processing unit and entered the S&P 500 within 8 years. The critical turning point that established the foundation for modern AI occurred in 2006. Nvidia released the Compute Unified Device Architecture, CUDA. CUDA was a proprietary application programming interface. It allowed software engineers to utilize the massively parallel processing power of GPUs for general-purpose mathematical computations rather than exclusively rendering 3D graphics. Nvidia deeply integrated this software layer with optimized libraries for frameworks that later became TensorFlow and PyTorch. They created an impenetrable 2-decade vendor lock-in. Software code written in CUDA physically could not execute on competing hardware from AMD or Intel without requiring fundamental, highly costly rewrites. Nvidia's ascent to absolute dominance was solidified by the strategic failure of its primary historical rival. In 2010, Intel officially cancelled the Larrabee project. This was an extraordinarily ambitious attempt to build a discrete graphics processor utilizing x86-compatible cores. Intel attempted to leverage its dominance in central processing units by forcing parallel computing through standard x86 architecture. The resulting chips were physically too massive and demanded excessive power. Intel retreated, essentially ceding the high-performance parallel compute market to Nvidia just as the deep learning revolution began. The mathematical viability of deep learning was definitively proven on September 30, 2012. During the ImageNet Large-Scale Visual Recognition Challenge, a team comprising Alex Krzyzewski, Ilya Sutskever, and their advisor Geoffrey Hinton submitted AlexNet. It was a convolutional neural network architecture containing 60 million parameters and 650,000 neurons. Training a model of this depth was historically considered computationally impossible on standard CPUs. The team utilized CUDA to parallelize the training process across Nvidia GPUs. AlexNet achieved a stunning top 5 error rate of 15.3%. It outperformed the closest runner-up by a massive 10.9% margin. This singular event proved unequivocally that the depth of a neural network directly correlated with high performance. It also proved that Nvidia GPUs were the only viable hardware capable of executing the requisite mathematics at scale. The trajectory of global computing was permanently altered. Realizing the existential threat of relying entirely on merchant silicon controlled by a single vendor, hyperscalers began secret, localized attempts at vertical integration. In 2015, Alphabet quietly deployed the Tensor Processing Unit V1 for its internal machine learning workloads. This marked the first successful deployment of a custom application-specific integrated circuit designed specifically to bypass Nvidia hardware. But the event that truly galvanized the entire technology sector against Nvidia was the failed acquisition of ARM Limited. Between September 2020 and February 2022, Nvidia aggressively pursued a $40 billion buyout of ARM from the SoftBank Group. ARM's instruction set architecture is the foundational intellectual property used by almost every technology company on Earth. Allowing Nvidia to own the foundational intellectual property required to build competing silicon would grant them an unassailable monopoly over all future computing. Regulatory bodies intervened. The US Federal Trade Commission sued to block the transaction, and the UK Competition and Markets Authority issued a blistering report citing significant concerns. The deal collapsed in February 2022. The failure of this acquisition was the starting gun for the hyperscaler rebellion. With ARM's IP secure from Nvidia's control, Amazon, Microsoft, and Meta realized they had a clear, unimpeded regulatory pathway to design their own custom silicon. In September 2023, this culminated in a direct assault on the software layer. A consortium backed by Intel, Google, ARM, and Samsung launched the UXL Foundation. Utilizing Intel's OneAPI toolkit, they engineered an open-source initiative specifically to break the CUDA software monopoly. The fundamental logic driving this concerted effort requires a deep structural understanding of the artificial intelligence compute lifecycle. The lifecycle is rigidly bifurcated into two distinct phases, with entirely divergent economic and physical requirements. Phase 1 is training. This is the computationally brutal process of feeding massive, unstructured datasets into a neural network to teach it foundational patterns. It demands extreme precision and ubiquitous hardware compatibility. In this domain, Nvidia's Hopper H100 and Blackwell B200 GPUs possess near-total hegemony. But training is a localized, one-time capital expenditure. The market has rapidly shifted toward Phase 2, inference. Inference is the ongoing process of serving a finalized, trained model to millions of live end users, requiring the continuous generation of tokens. It optimizes strictly for cost per token and thermal power efficiency. Because inference represents a permanent, scaling operational expense, hyperscalers are aggressively transitioning these exact workloads away from expensive, power-hungry merchant GPUs. They are routing them toward highly specialized application-specific integrated circuits housed within their own data centers. To execute this transition, the industry first dismantled the secondary moat securing Nvidia's monopoly, the software compiler layer. Hyperscalers standardized around open-source, hardware-agnostic compilers, most notably OpenAI's Triton language. Internal testing demonstrated that complex models can be entirely executed via Triton, achieving near parity with native CUDA kernels on H100 hardware. Absolute software lock-in is officially broken. Simultaneously, a third mechanical battlefield emerged at the networking level. Advanced AI requires clusters of tens of thousands of processors communicating instantaneously. Nvidia enforces ecosystem dominance through NVLink and NVSwitch. These proprietary interconnect architectures bind the entire server rack to a single vendor. To shatter this hardware perimeter, the industry formed the Ultra Accelerator Link Consortium. Heavily backed by AMD, Broadcom, Intel, Google, Microsoft, and Meta, UA-Link completely reframes the server rack. It establishes an open standard scale-up interconnect designed specifically for direct memory semantic communication between accelerators, bypassing the high latency of standard Ethernet infrastructure. Data centers can mix and match hardware from different vendors, directly neutralizing the NVSwitch integration advantage. With the software and networking moats compromised, every major hyperscaler is now deploying specific, uniquely engineered silicon mechanisms to route compute away from Nvidia. Microsoft unveiled the Maya 200 accelerator in late January 2026. Manufactured on TSMC's cutting-edge 3-nanometer process, it abandons heavy precision for raw inference throughput. Deployed in primary U.S. central data centers in Iowa, the Maya 200 powers OpenAI's GPT 5.2 models and yields a claimed 30% better performance per dollar metric compared to legacy Nvidia server instances. Meta accelerated the deployment of its third-generation Meta Training and Inference Accelerator, codenamed Iris, across its global data center fleet. Meta's core business requires hyper-efficient content ranking, making general-purpose Nvidia GPUs mathematically inefficient. The Iris chip natively optimizes for deep learning recommendation models, dedicating massive compute cycles specifically to embedding table lookups and ranking funnels. Amazon Web Services focuses on offering direct cost savings to end users via internal silicon. The Trainium 3 generation began shipping in early 2026. Coupled with AWS's custom Graviton CPUs, Amazon constructed a completely independent hardware silo that fundamentally bypasses standard merchant silicon. Apple bypassed the cloud provider wars to focus entirely on maintaining its closed ecosystem. Known internally as Project ACDC, Apple designed proprietary server-side inference chips to power its private cloud compute system, handling off-device requests for Apple Intelligence. Utilizing TSMC's new 2-nanometer N2 design process, Apple shifted massive capital to production facilities in Baoshan, Taiwan, bypassing the older 3-nanometer nodes in Phoenix, Arizona, to ensure absolute vertical integration on the bleeding edge. In the most significant structural shift of 2026, OpenAI, traditionally a pure software and research entity, transitioned into hardware design to secure long-term supply stability. Dubbed an XPU, Project Tigris is co-developed alongside Broadcom, with Broadcom securing over $10 billion in AI infrastructure orders from this new client. The chip enters mass production by 2026. It marks the exact moment the premier AI lab completely decouples from its foundational hardware supplier. The financial impact of this disintermediation is profound. In fiscal year 2026, Nvidia reported legitimate, extraordinary financial performance. Total corporate revenue hit $215.9 billion, a 65% year-over-year increase. Data center revenue posted $193.7 billion, constituting 91% of the business model. In Q4 alone, Nvidia generated $68.1 billion in revenue, yielding a net income of $120.1 billion for the fiscal year, while throwing off $97 billion in free cash flow. But by eliminating Nvidia's $33,600 hardware markup per unit and paying TSMC directly for the raw manufacturing cost, hyperscalers are creating a massive new economy. By Q1 2026, Amazon's custom silicon division achieved an annual revenue run rate exceeding $20 billion. Market analytics from Epoch AI confirm this rapid expansion, tracking Amazon's share of cumulative global AI chip shipments expanding to a highly disruptive 7.5% by late 2025. The resulting cloud computing landscape saw inference hardware rental costs plummet. By March 2026, independent cloud providers were offering spot pricing on mature hardware at heavily suppressed rates. The merchant silicon rental market is rapidly commoditizing. The conflict over AI silicon dominance extends far beyond corporate balance sheets, introducing immense geopolitical choke points. Whether Nvidia is fabricating the B200 or Amazon is fabbing the Trainium 3, the physical supply chain is bottlenecked by a single, geopolitically vulnerable entity, the Taiwan Semiconductor Manufacturing Company. TSMC commands roughly 70% market share of the global foundry business and a staggering 90% share of advanced sub-5 nanometer nodes. Crucially, they maintain an impenetrable monopoly on the specialized advanced packaging protocols strictly required to interlink logic dies with high bandwidth memory. Simultaneously, the physical realities of powering this massive global compute rollout are clashing violently with the limits of existing electrical grids. The International Energy Agency reports that global electricity demand from data centers surged by 17%. Total energy consumption of hyperscale data centers will double, skyrocketing to roughly 1,050 terawatt-hours by the close of 2026. If the global data center infrastructure were classified as a sovereign nation, it would be the fifth largest energy consumer on Earth. Financial models from the Goldman Sachs Global Institute predict that under rapid expansion scenarios, data center infrastructure could consume a staggering 7.4% of total United States electricity output by 2030, swelling to potentially 19.5% by 2050. To circumvent collapsing terrestrial power grids, Meta partnered with Overview Energy to pursue space-based solar power. By positioning generation satellites in geosynchronous orbit 22,000 miles above Earth, Meta aims to collect solar energy continually. beaming it back to terrestrial data centers via low-intensity near-infrared light. As the physical infrastructure expands, compute capacity has officially been reclassified by governments as critical national defense infrastructure, refusing to allow a single American corporation to dictate access to foundation models. Nations are aggressively pursuing sovereign AI. Saudi Arabia formally designated 2026 as the Year of Artificial Intelligence, launching the 480-megawatt Hexagon data center and injecting over $9.1 billion in venture capital toward AI firms. The United Kingdom simultaneously mobilized massive capital, funding the AI Pathfinder initiative and securing billions in AWS investments. By late 2026, analysts tracked over $100 billion, strictly allocated to sovereign compute commitments designed to construct independent, localized AI factories, completely insulated from foreign corporate control. This geopolitical fragmentation is exacerbated by aggressive global antitrust enforcement seeking to dismantle Nvidia's estimated 85% chokehold on the merchant AI chip market. In the United States, the Department of Justice Antitrust Division issued stringent civil investigative demands to Nvidia. In Europe, regulatory bodies invoked Article 22 to forcibly examine localized tech acquisitions. In China, the State Administration for Market Regulation ruled that Nvidia breached the country's anti-monopoly laws. Furthermore, geopolitical friction resulted in Nvidia absorbing a severe $5.5 billion charge for stranded inventory after the US government abruptly banned the export of modified data center chips to Chinese markets, permanently cratering a massive revenue stream. Recognizing the impending commoditization of raw hardware and the severe regulatory constraints on physical acquisitions, Nvidia aggressively pivoted to establish an unbreakable enterprise software monopoly via the NemoClaw stack, marketing it as the operating system for personal AI. The viral OpenClaw platform surpassed 250,000 GitHub stars in just 60 days, but the complex mechanics of deploying autonomous agentic AI quickly resulted in a catastrophic security collapse. In late January 2026, Maltbook, a massively popular AI agent social network built on the OpenClaw framework, suffered a devastating breach. The failure was not an advanced architectural flaw, but a fundamental database misconfiguration. Developers failed to configure row-level security, RLS, and exposed a hard-coded Supabase API key in their client-side code. This basic oversight granted unauthenticated read/write access to the entire production database, triggering a massive credential leak that exposed 1.5 million API authentication tokens and tens of thousands of private emails. The systemic breach forced immediate security lockdowns across major hyperscalers. Ironically, this catastrophic failure undermined the exact protection NemoClaw was built to provide. Earlier in the year at Meta, a vanilla open-source AI agent autonomously exposed massive troves of internal engineering data to employees for 2 hours, an event that had directly motivated Nvidia to build NemoClaw's enterprise guardrails in the first place. The incident completely fractured the trust required for enterprise integration. It critically stalled Nvidia's desperate pivot toward a high-margin, software-centric future. Nvidia was forced right back into the brutal physical arena they were trying to escape. And in that arena, the reality is terrifying. Because whether Nvidia builds the B200 or Amazon builds the Trainium, every single one of these tech giants is still completely trapped. They are trapped by the physical limits of the terrestrial power grid, and they are bottlenecked by a single, geopolitically vulnerable island in the Pacific. Every major technology giant is collectively deploying hundreds of billions of dollars to permanently rewrite the physics of global computing. The companies funding Nvidia's present are constructing the absolute certainty of its demise.